A lot of definitions before we get into the actual like calculations and stuff like that, which some of you like, some of you are not going to like. It's just the way it works. So, all right. So, chapter 2. The first thing we want to start looking at is like how we actually use data and those type of things. And I talked briefly last class about like the COVID vaccine and stuff like that, and why, even though I know the whole concept was a horrible experience for pretty much anybody that went through it. I was like, it was not a fun time to be alive and living and trying to work and everything else. However, it was the first time in probably like history that we saw in real time science, statistics, and everything else working in real time. Like, so most of the time when you guys took science classes or math classes and stuff, the teacher always knew the answer. It was like, there was one right answer. It was one way to go it. You went to a biology class, there's laws, there's rules, there's definitions. Like you learned this and everything was known. Science is messy. Statistics is messy. Everything is not known. The problem is that by the time it gets to you, typically it's gone through 5-10 years of research and development and information, so that by the time you guys actually hear about it, it's basically a known fact at that point. With COVID, everything was changing on a daily basis. And I think what happened was a lot of people are used to science being very cut and dry and math and stuff being cut and dry and the data being there. And when we saw it being messy, people are like, well, science is wrong. Well, no, it's not. This is actually how it works. So when we're starting to look at data like this class and stuff like that, you're now going to start to get that inner workings of how that stuff works because you saw it happen. Now we're going to understand why it happened that way. So one of the things that we're going to start looking at is literally like when you get data, how do you determine if that data is credible? How do you determine if it's good? And some things that you want to ask is, did they study it adequately? Or did they, when they looked at it, did they look at the right types of measurements? Did they look at the right information? Okay. And I think this is the part that was really messy in COVID. It's like it changed constantly. Like from when we shut down, we had no clue what was going on. We didn't know what was going to work. We didn't know any of that. People were literally doing the studies as things were happening to try to figure out what was going to be the best way to deal with it. And that's why by the time August and September came around, we were able to get back to schools and working, not normal by any stretch of the imagination, but we were able to have some people in the building and stuff like that because we had some more information about it. So having that concept, like, was it adequately studied? At that point, it wasn't. We needed time. Like I said, most research, 5 to 10 years. And they were doing it in weeks to try to get this information. Was the data measured accurately? And this is the thing where, like, the data that they had actually wasn't measured accurately. The data changed 2 days after they had that data measured correctly. And that's where that was hard. So, and was there significant quantity in the data to draw those conclusions? No, we didn't. We kept getting more and more data. And that's once we started getting enough data to really realize that, that's when we were able to start making some valid conclusions on what was going on. So one of the students in my last class says, like, shouldn't we have had this stuff beforehand? Like, shouldn't we have like had some processes in place before this happened to deal with it? Problem is we never really had a situation like that. So polio is a little different. And actually, the polio and the Spanish flu is probably the most closely thing. But polio had been around for decades. So the first polio vaccine was developed in the 1930s. And it killed people. People literally died from the vaccine. So they didn't use it. The actual polio vaccine that annihilated or that basically eliminated polio didn't come out until the 1950s. It's like 20 years between when it first started getting developed to when we actually started injecting everybody with it. So, and with COVID, they were trying to come up with it in 6 months. And that's where they needed that more data. The same thing, like when we had like the Spanish flu, which was in 1918, it was a lot different world back then. Even up until like World War II and stuff like that, the world was drastically different. Like the book actually has some statistics, and I looked at it. I'm like, actually, some of these are really interesting. The average life expectancy in the U.S. today is right around 73 years old. In 1903, which is where all these are from, it was 47 years old. I'd be dead. Okay. So it's like you start to think it's like, whoa, like that's huge. And then we're starting to talk about like Social Security and everything else. Where it's like, okay, we retire, like your Social Security is at 65 or 67 or stuff like that. It's like when Social Security first came out, people didn't live that long. Okay. Most of the times when you retired, you had 2-3 years left to live. So now we're living 20, 30, 40 years past the time people are retiring. That means a lot more money is needed. It's where you're starting to go run into some issues. 14% of homes had a bathtub. The maximum speed limit was 10 miles an hour. The average wage in the US, 22 cents an hour. I think right now, if you went back in that one, well, right now the average wage is somewhere around $20 an hour.
What?
Average wage, not minimum wage.
I was going to say.
Average wage. That's where this is the average wage. There was no minimum wage in 1903. 95% of all births took place in the home. You didn't go to a hospital. You had midwives that did it. 1 in 10 people were illiterate, which actually, that shocked me. I thought it would have been higher than that. And only 6% of Americans graduated from high school. Now 6% of students don't graduate from high school. They're asking you what's wrong with your school. So it's like you start to think about how different the world was back then to what it is today. And one of the, it's like, think about like the bathtub and stuff like that. Hygiene was drastically different. There was a lot more diseases and stuff back then. So we have a lot of science, a lot of data, a lot of medical research and advances and stuff like that that are keeping us alive a lot longer and are keeping us more healthy. But we're also living in a lot more sterile environment. So when those new viruses pop up, they're going to affect us a lot more because we don't have, our body's immune system doesn't have the antibodies to fight a lot of this stuff. So hopefully now we've learned and we have things in place that can prevent things in the future and better ways to deal with things in the future. But hopefully we won't have to deal with it for another 100 years or so, because that's about, seems like the routine at this point. So, all right. So when you're looking at data, those are some of the questions that you want to ask yourself. In all your years in schooling, when is the one place you've probably dealt with data? Use data. Mostly in science classes, actually. You probably dealt with a little bit in math class, but honestly, the majority of it, you probably did in science class when you did experiments and stuff in your labs. Yeah. Yeah, you do a little bit in history. History teachers try to stay away from math stuff. But a lot of it is in science, and you learn the scientific method. Okay? You gathered information about what you wanted to be studied. Based on that, you created a hypothesis that you wanted to test. Then you tested your hypothesis. And then that hypothesis in your experiment was repeated over and over and over again. And eventually, it becomes a law and accepted fact. Okay? Like I said, years, decades, sometimes centuries before things are completely and utterly supported. So it's like the whole concept of like the flat earth and everything else like that. It's like it was centuries before the community accepted that the sun was in the middle of the solar system and that the earth did not the sun did not revolve around the earth. Like they killed scientists because that's what they said back in the dark ages. So it's like, so it was centuries before some of that stuff that we accept today actually was accepted. So when we're looking at this is the process that they typically go through. Okay.
I like the $11 for the phone call from Denver to New York.
Yeah.
For a 3-minute call.
I don't think most of you guys even think about paying for a phone call anymore.
Yeah, it doesn't happen.
I still remember actually having to pay for phone calls. So, and the self plan that came with minutes of calls.
We used to, my relation living in Canada. So imagine the phone calls from Connecticut to Canada.
Yeah.
Yeah.
So yeah, it was a little crazy. Times have changed. You don't even pay for text messages. Text messages are now unlimited now too. We used to have like, you can only do a certain number of text messages. I remember actually putting a quarter, or actually not even a quarter, a dime into a phone call and saying, come pick me up. Or if I didn't have a dime, literally calling collect and trying to get it in before the operator yelled at you.
Those were the
Yep. So life has changed. Some things for the better, some things not for the better, depends on how we look at things. And I think with AI and everything else now that we've got going in, up until this point, we had computers that could help us crunch data and like do the analysis, but we would have to tell the computer what to do. Now with artificial intelligence, a lot of stuff that we're being able to just dump data in and have the computers actually determine what's going on and actually start doing its own data analysis outside of what the person's telling them to do. Google's actually started this about 6 or 7 years ago. They were actually analyzing, because one of the things you do with your phone is they have the cameras on the front of the phones to scan you in. It's looking at facial parts and your eyes specifically. They were actually using your eyes to determine disease. So they had started to notice that people that had certain diseases had defects in their eyes, and they were using the computers to start analyzing eye prints to determine that. And with artificial intelligence, it's now actually able to take photographs from all over and actually start looking to notice slight differences in the eyes in people that have certain diseases and stuff, to be able to use it as a forecursor to be able to say, this is something that could happen down the line even before you notice that you're actually sick. So, but 100 years ago, I'm pretty sure this would be creepy. So that's the thing. It's like, what's creepy now, once it becomes commonplace and used, becomes less creepy. So we're still at the age that we remember Terminator and Skynet. So it's like, that's our mindset. It's like, oh, wait. But technology advances. It's just a matter of how we get to actually use that technology. We use a slightly different scientific method. Well, it's called the decision-making method when we're looking at data and statistics. The first thing you want to do is clearly define the problem in any influential variables. So when you're looking at deciding something, it's like, okay, this is what I want to study. These are the variables that would affect what I want to study. Okay. We're then going to decide on what is my objective. So what's the goal? And what decision criteria I'm going to use. So how do I determine if what I'm going to use was effective or not effective? That part right there, we're going to do a lot more down the road. Chapters 9, 10, and 11, actually, that's the end, is where we're actually going to be looking at that decisions and making those hypothesis call and determining if what we did was accurate or not, or that actually had the outcome that we wanted. The next thing I think is probably the most important thing, and one of those things that we don't do very often anymore. Create alternative solutions. So you take your problem, this is what I want my outcome to be. So we're going to do my study and everything else, and we're going to hope that's the outcome that I get. But what are some alternate things that could happen? Okay, so when you just look at it from your perspective and your point of view, your data can become biased. And it's going to show one thing. By looking at alternate solutions or alternate options, you can start to say, okay, well, maybe this has happened instead of this. Let me look at my data in that lens. Okay. And sometimes it takes another person to look at it. And that's where, like the scientific method, they typically have more than one person having to recreate your study. This is where other people come in using their perspective and do it and see it. But you can do it yourself too. You then take your alternate solution using the same criteria that you did your initial one and say, okay, does this make sense? Yes or no. If it also makes sense, well, then maybe something's wrong with your data, or maybe something's wrong with your initial conclusion. If multiple things could possibly work. So that alternate solutions thing, I think, is very important. It's like getting different perspectives. And if you're working on a team, having everybody come up with different ideas is very important to that respect. Okay. I think that's the key piece in that. It's like looking at those different perspectives, and it helps eliminate that bias piece that we want to eliminate as much as possible. All right. So influential variables are the ones that we're going to look at that we think are actually going to influence my study. We have other variables. Sounds like a Harry Potter variable, like a spell, like from Harry Potter. Confounding. Confounding variables are extra variables that you did not think about, and that can cause your data to become skewed. This is the type of variables that we talked about when I was talking about the COVID vaccines in the first class. We were looking at how it was really effective in the trials, like 95% effective. And then when it went to the mass public, it was in the 70s or even lower in some, depending on the vaccine. Those confounding variables that they didn't take into account: masking, social distancing, did they leave home? Were they working from home? Did they go out to a restaurant? Those type of things. Those were all those extra variables that they didn't take into account. They looked at just the vaccine and nothing else. And those impacted the results. So sometimes you don't recognize those variables until after you're done, when the data didn't come out quite the way that you thought it was going to. And then you start to look at, well, what could have caused this problem? It's like what ended up happening with the COVID vaccine is going back and looking at alternate reasonings. They didn't do that either because they didn't have time. So what they ended up doing was they used their bias because they thought their vaccine was going to be very good. And when the results came out and showed that the vaccine was very good, they were happy. They didn't look at those other options because, again, they didn't have time. They were literally under that massive time crunch to get these out to save people. So these are some of the things that you want to keep in mind when you're looking at doing either your own research or looking at what other people have done. So when you look at it with your perspective, it's like, did they look at this? Did they think about that? And if they didn't, that might have skewed their information. And sometimes in the reports, they'll explain, like, yes, we looked at this. This is why it didn't matter. It's like, okay, they looked at it. They thought of that option. All right. We're going to talk about graphs a lot next week. But these two graphs showed up in the book. And I want to briefly talk about them. So the first graph is about late deliveries. And the second graph is about a patient's temperature history. I will tell you that the first graph, actually, before that, what do you get from that first graph? The upper graph. With some, because they say a picture's worth 1,000 words and a graph is a picture. So yeah.
I would say kind of like over time, like let's just say like if those are like years, like
well, they're weeks, but yeah,
like weeks, but like to see like if it changed over like a long time, then compared to the second one, it's more like precise to see if there's a difference in a small period of time.
Okay. Well, don't look at the comparing the two graphs. Don't do that because they're completely different data and everything else. So just look at the top graph with some. Yeah.
So it is late deliveries each week.
Mhm.
So like the first week, it was okay, they're not that late. Second week, it went up. Third week, it went down a little bit. Fourth week, it went down, but then it just like skyjacked from the fifth and the sixth week.
Yeah, like if you're looking at that, like that's typically the general trend, right?
Right.
It's going up. Okay. So, like I said, we're going to talk about graphs a lot more. There's a few things that are very interesting about this graph. First thing is it doesn't start at 0. It starts at 6 and goes to 15. So it doesn't start at 0. So you have it extends that look there. So that's one of those things that keep in mind when you're looking at graphs. Second thing I want to talk about in a minute. Let's look at the patient's temperature history. For all those in healthcare, is this person sick? Yes. Their temperature is definitely going up, but it starts at 99.4 and the max is only 100.8. So it's only going up by 1.4 degrees. Okay, which over 11 hours, or actually over 5 hours, is probably a lot. But it's like, it's not like they're going from like 98 to 105. It's like so looking at how they do that side piece, that can influence what you're looking at. Okay. All right. So between hour 7 and hour 8, at any point, was it 100 degrees? Was their temperature 100 degrees? Between hour 7 and hour 8. Well, yeah, because they started off at 99.6, right? And they ended up at 100.1. So at some point, it had to be 100, right? Because they don't just jump from one temperature to the other temperature. The temperature changes gradually, and it can change quickly, but it has to hit everything between it. Is there somewhere between week 4 and week 5 that there was 9 deliveries late?
Yeah.
Which day? Or which week?
The fifth week. Well, between the fourth and fifth week.
But it's late deliveries each week. So in week 4, how many deliveries were late? About 7, right? We'll take that 7. In week 5, there was 10 deliveries late. Right? Is there a week between week 4 and week 5? Right, still the 4th week, right? It's not telling you late deliveries by day. It's saying late deliveries each week. So week 4, there was 7 deliveries late. Week 5, there was 10 deliveries late. This line in between here means nothing. Okay? So that line, let's see if it's next slide. Nope. When you, and everybody in here has done it. You can't deny this. Everybody's done it. Whenever you put dots on a graph, you connect them. No, whenever you put dots on a graph, you connect them. Inevitably, you connect them. Okay? That connection means something. All right? So by connecting the week 4 and the week 5, you say there's information between week 4 and week 5, but there's not. Okay? There shouldn't have been lines on that graph. They didn't even talk about it in the book. They literally put that graph there. It's a horrible graph. There should not be lines on it because that line doesn't mean anything. In the patient's temperature history, it does. Okay, because there is something between week 7 or hour 7 and hour 8. They measured it at hour 7 and measured it at hour 8, but there is stuff between there that means something. And it had to go through all those other temperatures between there to get there. Between week 4 and week 5, there wasn't any time when there was 8 missing deliveries or late deliveries because it's a week and a week. Yes. You could do a bar graph. You could literally just do dots. Okay. You actually absolutely could have just dots on it. So you could have just put the dots there. And that would have been a totally valid graph. And even without the lines, it would have shown you the same stuff. Okay. You don't necessarily have to have those lines there. A bar graph is typically more common what they would have done. But that's the thing you want to look at is when you're looking at, don't automatically connect dots. It's one of my little pet peeves with line graphs because everybody wants to do it. Lines mean something. We're going to actually talk about another term in a little bit that's going to connect back to these graphs. Actually, we're going to do it now because I actually think it makes more sense to do it now. All right. There's two types of data. There's discrete data and there's continuous data. Discrete data has a specific set of values. Okay. And there's typically nothing between them. All right. So the late deliveries was discrete data. You had 6 late deliveries, 7 late deliveries, 8 late deliveries, but there couldn't be 6.5 late deliveries. Okay, there couldn't be 6 1/3 late deliveries. Okay, they were discrete pieces of data. The temperatures, the patient's temperatures, were continuous because everything between those numbers also made sense. Okay, there is information between 99 degrees and 100 degrees. Okay, that has value, that has information. And to get from 99 degrees to 100 degrees, you have to go through everything between 99 and 100 degrees. Okay, so that's continuous. When you're doing a line graph of continuous data, connecting the dots makes sense. When you're doing a line graph of discrete data, connecting the dots does not make sense. Okay. Yes.
What's an example of continuous thing?
Your height is continuous. Okay. You cannot jump from 4 feet to 4.5 feet. Okay. You're at some point you were 4 feet 1 inch. And at some point you were 4 feet 2 inches before you got to 4 feet 6 inches. Okay. So that's continuous data. You're going to go through all those. Blood pressure. Somebody brought up in the other class that it was discrete. Same concept. It's continuous because there's values between it. We typically don't talk about them, but that doesn't mean they don't exist. So when you're looking at the little blood pressure machine, its dial is going up continuously. It's not jumping. Okay. If you have a clock, like most clocks now have that smooth motion, but there's some clocks that don't have the second hand that the minute hand will jump to the minutes. That would be a definition. That would be a showing of a discrete thing, even though we know time is continuous. The way that it's showing you, it's jumping between it. That's more of that discrete concept. Time and typically in general is continuous because you can break it down more often. Shoe size. Is shoe size continuous or discrete? Why is it continuous? Okay, why is it discrete? Okay. The people who said discrete, listen to my question very carefully. The people who said continuous thought of feet. Shoe size, discrete. Feet size, continuous. Your foot grows. Shoe size has very specific shoe sizes. They do have halves. So typically I'll say if you can cut it in half, it's probably continuous. Shoe size is one of those weird ones. You can get a 4.5 size shoe or 7.5, things like that. You can't typically get a 7.25. So shoe sizes has very specific values that you get your shoes at. All right. And those make it discrete. Okay. If you're one that likes to wear hats, snapback hats, continuous, because you can set them pretty much anywhere. Okay. Or this actually is Velcro. I can literally set it anywhere. The fitted hats, discrete, have very specific values. Okay. They have a lot more than shoe sizes do, but they're still very specific. Unless you go to a, oh God, what's the name of the hatter? There was a name, and I can't think of it. A person who makes hats, they actually can make it exactly to fit your head for any size that they want. Crazy little thing. Do you know why the Mad Hatter was mad? Yeah. They used to use mercury to create hats.
Really?
Yep. It was mercury poisoning. So, yep. All right. So let's talk about collecting data. There's two ways to collect data. You can have observational data, or you can collect data through a controlled experiment. Give me some examples of observational, how you can collect data through observation.
Like color wise, maybe?
Yeah, you could observe the colors and pick the colors. Okay.
I could count how many people are walking by, but I'm not like sending people. But
Yes, that's observation when you're looking at it. Yes. Okay, so we're not looking at types of data. We're looking at like what type of like thing you would do when you're collecting that data. So like when he's looking at people walking by, he can collect data about the people walking by. That's observational. When you were in high school and stuff like that, when the administrator came into your room, that was observational data. They were observing the class to write information down. Yeah.
Like observing information out in the wilderness, like
Yeah.
observing animals in
Yep.
their habitat.
Yeah. Surveys are observational data. Okay, you're collecting that data. It's not the same way as you're using your eyes, but it's still observational data. There is certain situations where the act of observation can change the behaviors, especially in nature. If you're physically there looking at it, that can change the behavior of animals. So we want to find ways to observe without interfering. Whenever an administrator came into a class, it definitely changed the observation of the class. When I cared, I made sure that my students knew they were coming in, made sure that I bribed them sufficiently and everything else. And when I didn't care anymore, I just said it doesn't make much difference. But that was observational data. So most of the data that you guys would do on a daily basis or thinking about things, you would look at it as observational. Rarely are you guys doing controlled experiments. When you were in science class and we're doing your labs, most of those are controlled experiments. So controlled experiments are where you are trying to eliminate as many outside variables as you possibly can to collect the data. Okay. So let's see what it is. When you're doing a controlled experiment, there's two types of variables. You have your response variable. Your response variable is what's the outcome? Well, it's measuring the outcome. So it's what you're looking at. Okay, so it's what are you looking at in terms of your study. Your explanatory variable is what's the reason for whatever the change is in the response variable. That's your explanatory variable. So what are those changes that were made?
So what's the controlled experiment?
Controlled experiments where you control all the information. Like when you're trying to make sure that there's nothing outside that's impacting it. I'm actually going to talk about one in a second. So the observational ones is ones that you typically, that's what everybody recognizes. A controlled experiment is typically ones that are scientists are doing in natural environment where they're saying, this is the process that I'm going through. This is the things I'm studying. These are the participants I'm looking at and that type of stuff. So a controlled experiment would be if we're looking at the size of fish. So, or the number of fish in the pond. They'll go through, they'll grab a bunch of fish, they'll tag them. Then they come back to the same area, they fish up a bunch of fish, they count how many are tagged compared to how many aren't tagged. That's actually a controlled experiment because they're doing it in a very defined area, looking at what's that change in that area. Observational data would be if they were just looking at, like they were actually counting, like looking at the observing and saying, oh, yep, there's more fish here today than there was yesterday, those type of things. All right. So here's we're going to do make genetically engineered tomatoes to increase their yields. Now, this is one of those crazy things that have drastically changed over time. We see GMO now and we go, oh my God, that's horrible. I want everything organic. Organic doesn't exist. I hate to tell you. Everything's been genetically modified or engineered. Okay. The reason we have so much food today is because they were genetically engineered. Now, the difference is, were they genetically engineered in a lab, or are they genetically engineered by breeding habits and by design? Most food over time has been genetically engineered based on breeding and cultivation, where it was done in a way where the whole concept of the strongest survives. We want food that's going to last longer. We want food that's going to grow faster. So when they found a breed of corn that was going to grow faster, they crossbred it with another one that was going to do this, and it grew faster and bigger and those type of things. They do the same thing with animals all the time. If you're looking at getting a specific type of dog, most dogs today are a function of breeding and genetic breeding to specifically get certain things. So for the wonderful example, hold on, just because they're my kids and I have to show them off. I want a picture of the two. Nope. Trying to find a good picture of them. Oh, actually, I have a good picture this way. So I have two corgis. Actually, I have two corgis. I love my corgis.
I'm glad you called them your kids.
Yeah, they're definitely my kids. Here we go.
Oh.
So those are my babies.
Is
so-
one in lab?
Yeah, it's a lab Dalmatian mix. So so that's Waldo, that's Star, and that's Levi. So I have two corgis. Does anybody know what corgis were actually bred to do? They're herding dogs.
Really? They're itty bitty legs?
Yep,
Really?
they're herding dogs. So corgis were bred to herd cattle, like cows. The reason they don't have a tail is because it was genetically bred out because the cows would bite the tails to grab the dogs. So they bred the dogs so they didn't have a tail anymore. They're also the reason we have the term ankle biter, because they would bite at the ankles of the cows to get them to run the direction they wanted to run. That's why those small little dogs. And believe it or not, corgis are insanely fast. They might not look like they're fast because they have little short legs, but they can move.
Yorkies are like that too.
Yeah.
And they were bred to hunt rats.
Yeah. Yeah. So you'd be amazed. Like the stuff that we have, like that we're looking at, like, oh, it's so cute. It's like there's reasons behind that it was done that way. It was genetically engineered. All right. So now off on that little thing. Let's talk about this problem. So we've made this new species of tomato. We've genetically engineered it to increase the yields. How are we going to determine if it produced higher yields? What kind of study are we going to do? Are we going to do an observational study or a controlled experiment?
Observation.
So if we did an observational study, how are we going to, what are some of the things that could impact the actual study?
Weather and the environment.
Yep, a lot of those things, right? So if we're just doing an observational study, we don't have control over those. So we're going to kind of do some kind of controlled experiment. So the question is what things are we going to have to control? So we talked about weather. What's specifically in the weather? Rain, the water, and sun. Okay, those are probably the two things that we're really going to have to figure out. Anything else? Soil types? Yep.
Environmental.
Temperature? Okay, so yeah.
I was going to say like animals.
Yeah, we don't want critters and stuff like that can come and definitely affect things. All right, so we're going to set up a controlled experiment for this. How are we going to do it? How are we going to control those aspects? So we can use a greenhouse. One greenhouse or many greenhouses? Okay. How do we make sure that each of the greenhouses are exactly the same?
I think you should use that one.
If we use one, we have less variables. Yes. Yeah. We use one, less variables, less things that we have to worry about. So we use one greenhouse. Yes, it'll be a decent sized greenhouse, but we can use one greenhouse. Okay. So the greenhouse takes care of what? We can keep the temperature consistent, right? There's no real rain in the greenhouse. We're going to produce the water ourselves, right? The sun, since we're using one greenhouse in one location, the sun will be the same for all the plants. And
We're producing the soil.
we're producing the soil. They're not going to be just in the ground, so we can control that. So that's how we're going to do it. And what typically ends up happening is you would do something like that. You'd have your plots of different things. So now that we've controlled the environment, we've controlled all the information. This is a controlled experiment. We would plant all our tomatoes, and then we're going to still observe to get that information. So even though we're doing a controlled experiment, doesn't mean we're not observing. We observe to collect the data. The controlled experiment is where we start with. We're controlling the aspects of the experiment. Yeah. Not that necessarily want the desired outcome. So we control it to the point where we want to know that the one thing that we're looking at is what is causing the outcome. So in this case, we want to know that the genetic engineered tomatoes produce more than the other ones. Okay. So if we just planted them all out in the field and we didn't care, one area of the field could have better soil. So that could have been the reason that one gave a better yield. One could have gotten raided by wolves overnight and destroyed all the tomato plants. I don't know. One could have gotten more sun because there's shade trees over here that impacted it. So by just having them out in the field without having that control, we don't know, was it the genetic engineering that what we did to that plant that made it give more yield? Or was it the soil, or was it the rain? We don't know. By controlling everything except for the one thing that we're changing. So we'll have, say, 4 of those would be 1, 2, 3, and 4 would be my genetic engineered ones. 5 through 16 could be just other tomato variations that I have. Since everything is going to be identical except for that one change, I then can determine, okay, if plots 1 through 4 came out better and produced more than plots 5 through 16, I know it was my genetic engineered tomatoes that did it and not something else. Does that make sense? So it could be that 1 through 4 die. And the other ones didn't. And it was like, okay, well, obviously this didn't work. This did not give me the results that I wanted. So it doesn't necessarily mean you're going to get the results you want. It means that you're going to be able to tell if it was or not. Yeah. All right. There we go. Like there was another slide there, I swear. How would you determine if an SAT prep class improves performance on the SATs? Okay. What kind of data would you collect? Yeah.
The amount of students in the course.
Okay. Yep.
SAT scores of people that took the preparation course versus
Okay. So let's say I have the course I did. I have 30 people in the class. They take the SAT and they get a score on it. How do I know that it improved their performance on the test?
if they took it.
Yeah. But how do I know they improved?
So they have to take that and take the course.
Right. So this is where, and one of the hardest things about this class, I will tell you right now. Remember I said this last class too. It's not the math, it's the English.
Which sucks.
it's the English. It totally is the English. It's how things are worded and how things are used. So it's not does the SAT prep course give you a certain score? It doesn't improve the SAT, the performance. So to do that, not only do we need to know, did they do better, or not necessarily did they do better. I don't even care if they did better. I want to know if it improved their scores. So we would need them to take the test before and after, right? And see if their scores improved. However, everybody's scores improve if you take the test the second time. It's actually, there's enough data out there that shows you get a between 100 and 150 point increase in your SATs the second time you take your SATs. Okay, just because you actually know what to expect. So I need to know that my test did better than that. So that's what I'd be looking for. I'd look at the population of people who took the test twice. So we're going back to that population and sample, right? I'd look at the population that took the test twice. How much did they improve on the test? I'd take my
Chapter 1.
kind of. This is all going to rotate through. These definitions don't go away. The reason we're talking about them is because we're going to continue to use them. And that's why I said that's actually the important part, is that the more we start to use them, you'll start to get a better understanding what they are. So they're not just unique things. It's, in this case, my sample is my preparation class, right? It's a subset of that population. And I'm going to look at, okay, did my sample do better than the general population did?
Wouldn't you have to have like another group of people who take it twice but didn't take the preparation?
Well, yeah, that's what I'm saying. You look at the general population, there's enough people out there that have taken the test twice that you have that data is already there. Like I can go online and look at that's how I said, I know it's between 100 and 150 points. Because that data is already out there and analyzed. I then would take my SAT preparation class, that the smaller sample group, whatever I'm looking at, and go, okay, did my students do better? If my student scores went up by 200 points, they did better. My preparation course works. I then sell it to everybody else, make them all do it, and make lots of money. And that's actually how almost all like programs that get into schools work. Yes. I would never give you this question on a test. Okay, because this question is literally open-ended on purpose to talk about it. Okay, so no, I would never give you a question like this on the test.
So what is the answer to that? Yes.
So I would set up, the question actually was, what kind of experiment would you set up? You can set up an observational study. That's fine. You can do that. It's actually closer to a controlled experiment because I've now taken a specific group of students. I'm going to do something with that group of students. Excuse me. I have had them take the SATs beforehand. I'm going to do something with them, and they're going to take the SATs afterwards. It's known as a longitudinal study, where you're looking at the same group of people multiple times to see improvement or decline or whatever else you're looking at. In this case, I'm looking for improvement. I would then compare that to the general population to see if it improved more than the general population would have improved. So this would be a controlled experiment in that respect, because I'm trying to control as much of the outside influences as possible. So I'm not going to just look at my student, like take the test, get the SAT scores, and then compare it to another class that didn't take it because the students are different. If the students in that other class just didn't care, or the students in the other class were AP students and did amazing compared to my students who really didn't want to really put in much effort, I'm not going to be able to tell that. The key with this one was understanding that I need to give them the test first to be able to show that improvement. So, okay. All right. What's a placebo? Everybody should have heard this term at some point in their lives. Okay. Yes.
It's nothing.
Yes.
Basically a capsule with like this.
It's a sugar pill mostly. Most of the time, it's just a little sugar pill. So the placebo effect is when you believe something is happening to you, even though nothing is. Okay. It's typically, a lot of times it's medical. And if anybody in here is super religious, I apologize for what I'm about to say. It has a lot of times, this is where it comes into play, where it's like you have a bunch of people just praying over you and everything else, and you feel like you're going to get, and you get better. It happens. Okay. That's known as a placebo effect. Your body, the body is an amazing thing, and it has the mind and body has amazing to do amazing things that we still do not understand to this day. Okay. So that effect, even though there's no medical treatment in there, is known as a placebo effect. They do that because in controlled experiments, I want to know if what the medication that I'm giving is giving that effect. So if I have a control group that doesn't take anything and doesn't know what's going on, I don't know if that placebo effect is coming into play. So by giving the control group the exact same, so the control group doesn't know that the control group, they just think they're another person in the study. And that's what happens in most medical studies. You have 100 people, there's 50 people getting the treatment, 50 people not getting the treatment, but they're all being treated the exact same way. Okay, the only difference is a pill. One's getting a pill that actually has the medicine in it, one's getting a sugar pill. And I'm looking at the differences between those groups. So if the control group gets better over 10 days and the actual experiment group gets better in 5 days, I know my medication worked. Okay. Notice both groups got better. It just took the other one longer, depending on what type of study I'm doing. So that's why you have that placebo, is to basically rule out the fact that your body actually just gets better on its own because you think it's getting better. Okay. Does that make sense? Yes.
Would a placebo be like a base?
A what?
Like a control?
Yeah, your placebo normally is in your control group. But like I said, the control group's got to still think, they can't know they're the control group. Because so like a lot of things, when they're doing medical research, they're trying to like make people who typically are very sick better. Like that's why you're doing it. So if you're asking people to be in the study and you've got, say, 100 people who have cancer and you're trying this new treatment to help them, and you're saying, oh, by the way, you're in this group, but you're not going to get anything. Like that's going to depress them and everything else, which possibly could cause more harm. So it's like, that's where that control group is like, you have to do it in a way that isn't going to impact the study. And that's where another term that you will hear often is your double-blind study. So you're blind. So you have a couple different types of ways studies this. The blind study means that the patient doesn't know what's going on, but the doctors do. Okay. That can be good or bad, depending on what you're studying. If the doctors know you're not getting the medication and this person is, they might treat you differently. And that could impact that. Again, remember, we're trying to control as many variables as possible, right? That's the point of a controlled experiment, controlling those variables. So if you add in the variable that the doctor knows and that they unintendedly, they might not even do it or unintentionally, will treat people different based on that. It's like, I know you're not supposed to be getting better, so I'm not going to expect you to get better. I know you're supposed to be getting better, so I'm going to expect you to get better. And I'm going to treat you to make sure you get better. So that can impact that. And that's where the double blind comes into play. The double blind, the person doing the actual treatments, they don't even know who's the control and who's not. So that eliminates that ability of them to treat people differently. They're going to assume everybody's getting the medicine and treat them all the same because they're all going to be getting better. And when they start to realize that one group's or this person's not getting better and this person's getting better, they're going to start marking those things down, not because they know who's the control and who's the medicine, who's got the medicine. It's that gives the person who's doing the actual study information. Because for all you know, the person who's getting worse is taking the medication and there's something wrong with the medication. So you want that data. And by not knowing what it is, you'll start to get that information. So by having the double blind study, you get more control over your actual study. Okay. So again, everything that we do when we're doing these studies is to eliminate as many of those confounding variables as possible. Okay. Because that's the stuff that's going to skew your results. All right. If you ever get migraines, they suck. And there's lots of things that can trigger them. A friend of mine, her daughter, actually had her migraines triggered by red number 5.
Really?
Yep, that was what was triggered. They figured it out after, because honestly, that's something extremely hard to figure out. They figured it out after eating Skittles.
Oh.
It was Skittles that she ate, and they're like, and she got a migraine. And then she would eat something else, and not she would eat like some, or she'd eat some Skittles and wouldn't get a migraine. She does other times she'd get a migraine. And when they ended up so the doctor said, okay, we're gonna split the colors. And they found when she ate the red ones, she got a migraine. So, because they started saying you have to write everything down that you're eating, like everything. And that's what they figured it out. It's very difficult to figure out. Chocolate actually is one of those triggers that triggers a lot of people's migraines. Luckily, not mine, because I like chocolate. Yes.
I don't know if I ever had a migraine, but like, what does it feel like?
Like your head wants to literally
Explode.
Your eyes want to pop out of your
Lights
head
hurt,
and your
sounds
head
hurt.
wants to explode.
Yeah. So typically your migraines will happen right behind your eyes. But it's basically no, not a twitch. It's almost like you get an extreme muscle spasm where your muscle like really, and then for like hours afterwards your muscle's sore, but not like that's what it is. Like it's basically your brain spasming. It
Like, you want
hurts.
to wrap it with pressure.
Yeah.
You want to hold your head really, really tight.
Yeah.
Like,
Oh, okay.
yeah,
I know
it
that.
just hurts.
Yeah, it hurts. So the studies were trying to determine if chocolate can trigger migraines. So 12 migraine subjects were given peppermint-laced chocolate candy. They were given peppermint patties. And 8 migraine-prone subjects were given peppermint-laced without chocolate. But they have to look the same. That's the thing about with a placebo effect. The objects have to look the same. So the only difference between the two would be the cacao, which makes it chocolate. Okay, the other two pieces, they basically have to look identical. Otherwise, people are going to know. Okay, so 5 subjects from the group given chocolate developed migraines, headaches in one day. No one from the group given the placebo developed a migraine in the same time period. All right, which phase of the scientific method best describes the study? So think back to your scientific method, right? Yeah, we're conducting the experiment. This is the experiment stage. We already have the hypothesis. We're now conducting the experiment. Is this an observational study or a controlled experiment? This is controlled. They have all the stuff. They've got the placebo. They've got the control group. They've got the active group. Okay, so it is definitely a controlled experiment. What's the response variable? Migraines. That's what we're studying. The explanatory variable.
The reason why chocolate is a migraine?
Actually, it's chocolate. It's just the chocolate. So the chocolate. So the response is the migraine. That's what we're studying. The chocolate is what caused the migraine. That's what we're trying to determine. So that's the explanatory variable. Which group's the treatment group? The one eating chocolate, and the control group is the one not eating chocolate. Okay. So what's the population?
All of them.
Huh?
All people.
Migraines. People who have migraines. Okay. So migraine prone people would be the population. No, in general. So remember, population is large. So migraine prone people is the population. So that's all migraine prone people. The sample is the 12 people, or wait, sorry, actually 20 people, because there's 12 and 8. So the 20 people is my sample group. That's the sample that I've chosen to do this study on. Now, based on the study and the information I gave you, you can study that chocolate is a trigger for migraines. Might not be for everybody. Everybody's different on what triggers their migraines. Mine's weather. When the pressure drops, I get a migraine. So, but that's the thing. It's everybody's a little bit different in that respect. All right, we talked about discrete continuous data. And we are going to do that next class. The other problem, like I literally thought I was covering all chapter 2. And then I'm like, I realized afterwards, I'm like, I have 2 days to do this. So we are done.
Those two words right there, that's off the board.